Here is the next example. Here also he's asking about find the transfer function. So the transfer function here is h of t equal to v naught of t over v in of t, okay, which is a voltage gain in this case. As I mentioned in the previous video, S equal to j omega. So I'm going to use S instead of j omega. At the end, if needed, you can convert it back into j omega. Now, so this is 6 Henry. When you convert it into S domain or j omega, this is 6S. This is 1 over S times 0.25, which is 1 over 0.25. Can I write this as 4? So I can write this as 4 over S. Okay. Now, how am I going to achieve my goal? What I can do, I can find this impedance. Let me make that as some Z. Okay. So I have 6 ohm and impedance Z. Those two are in series, right? Now I can use the voltage division rule. I can find this V of Z. What is the formula for V of Z? As long as we know V input, as long as we know V input, that V of Z equal to V input times same impedance over total impedance. That is the formula to find the voltage across across an impedance if they are in series. And here we can have more than one impedance in series, it doesn't matter. Okay, so this is the way I'm going to find. Now once I find the impedance across the Z, now again I'm going inside the Z. Inside the Z I have two parallel paths. One is resistance, another one is capacitor reactance, another one is inductor. Okay, now I know the impedance here, V of Z. From this I can find V naught again by using the voltage division rule, because in parallel voltage is same, so the voltage across this must be V of Z. From there, how do you find V naught? V naught equal to V of Z times the same impedance, whatever this value is, or over R plus whatever this value is, 4 over S. 4 over S. So V naught over VZ. This VZ already had V in. Okay, so you can get the transfer function from the final equation. So I'm going to use the voltage division rule in this example. So in step 1, I converted the circuit into S domain. So here is an equivalent circuit. Now my main goal is find this total impedance there. Okay, so to find the total impedance, I'm going to call this as ZY. Okay, what is ZY? ZY equal to, those two are in series, 6 plus 4 over S. So if I simplify it, it is 6S plus 4 over S. Now the total Z, let me call this as ZX. This ZX is nothing but 6S parallel with ZY. Okay, so 6S times ZY over 6S plus ZY. If I substitute ZY, 6S times 6S plus 4 over S over 6S plus 4 over S. In the denominator, I'm going to find the LCM, which is going to be 6S square plus 6S plus 4. Here also I'm going to multiply the numerators. So 36S square plus 24S over S. Now SS get cancelled out. I end up with ZX equal to 36S square plus 24S over 6S square plus 6S plus 4. Okay, that's ZX. Now I'm going to find the total voltage across this. I'm going to call that as a Vx. Okay, Vx equal to V of x equal to total voltage Vn times Zx over zx plus 6. Okay, because as I mentioned, the 6 ohms is in series with zx, so in series voltage is going to divide. I already have the zx, so vx equal to vn times, I'm going to substitute zx there. So here I substituted zx value, so zx is nothing but 36s square plus 24s over 6s square plus 6s plus 4. Same way in the denominator I substituted zx. Now since I'm adding plus 6, I have to do the LCM, common factor, which is 6s square plus 6s plus 4, and I found this mathematical equation. You can verify the calculations. I'm going to pause it here for a second. Now the Vx equal to Vn times 36s square plus 24s over 72s square plus 60s plus 24. This is our Vx. This is not our V output. So if you look at the circuit, the V output, again I have to use the voltage division rule. Okay, so my V output equal to Vx times same impedance, which is 6 over total impedance, 6 plus 4 over s. Okay, so I'm going to copy this down there. So V naught equal to Vx times 6 over 6 plus 4 over s. If I simplify this, Vx times is 6s over 6s plus 4. What I did, I moved this s, basically I found the common factor. Okay, so I moved this s to the numerator, so I end up with 6s over 6s plus 4. Now I'm going to substitute this Vx right there. So V naught equal to Vn times 36s square plus 24s over 72s square plus 60s plus 24. Now this times 6s over 6s plus 4. Okay, now here in the numerator, see if I can pull out the 6s plus 4. If I pull out 6, or if I pull out 6s, isn't it 6s plus 4? 36s square plus, yes. Okay, and I have another 6s over 72s square plus 60s plus 24 times 6s plus 4. Now I can cancel out these two. Okay, now is there any way can I pull out 6 here? I can pull out 6 in this denominator. So 6s times 6s over, if I pull out 6, which is 12s square plus 10s plus 4. Okay, 6 get cancelled out. So I have V naught over Vn equal to 6s square over 12s square plus 10s plus 4. Even if I further simplify, V naught over Vn equal to 3s square over 6s square plus 5s plus 2. Okay, this is the transfer function of the given circuit in S domain. Now if you want to, you can substitute s equal to j omega. So h j omega equal to 3 times j omega square over 6 times j omega square plus 5 times j omega plus 2. We know that j square is nothing but -1. So if we substitute j square equal to -1 minus 3 times omega square, which is -6 omega square plus j5 omega plus 2. I think in the homework I want you to write it down in the form of j omega. Okay, in the previous case, in the previous video, I forgot to transfer that into j omega. I just left it in s term. Okay, please, in the homework, when you're solving the homework, please at the end convert that into j omega. I'm going to solve one more simple example here. Here is another example. I'm sure probably this might be one of the homework examples. So I mean, watch this video before solving your homework. Now, the transfer function, here he's asking about V0 over Vn. The circuit is in still time domain. I'm going to convert this into S domain. So this is 2S, this is 1 over S. Okay, I can see these two are in parallel. That parallel combination is in series with this. Now I can use the voltage division rule. So first thing, these two are in parallel. 2 parallel with 2S, that is going to be 4S over 2 plus 2S. If you want to simplify, it is going to be 2S over S plus 1. Okay, now I'm going to find V0. Okay, V0 is the voltage drop across this whole combination. I can use the voltage division rule. V0 equal to Vn times same impedance 2S over S plus 1 over 1 over S plus 2S over S plus 1. Okay, now I'm going to simplify. So V0 over V input equal to, in the denominator I have S times S plus 1. Okay, so there is no common term, so I have to multiply the 1 with S plus 1 and 2S with S. Okay, so it's going to be 2S over S plus 1. Now V0 over V input equal to 2S over S plus 1 over here 2S square plus S plus 1 times S plus 1. S plus 1, S plus 1 get cancelled out. So V0 over V input equal to, now I have S in the denominator of the denominator. Okay, so if I pull the S up, it's going to be 2S square over 2S square plus S plus 1. Now convert this into omega. So V0 j omega over Vn j omega equal to 2 times j omega square over 2 times j omega square plus j omega plus 1. So this value is minus 2 omega square over minus 2 omega square plus j omega plus 1. Okay, that's the transfer function for the given circuit. I'm going to solve one more example, simple example in this video. This is another example almost similar to the previous example. I think the previous example I have something in series with the 2 ohms. So if you look at here, no, it's the same example. It's the same example, but I'm going to modify it a little bit by taking the output voltage across the capacitor. So now instead of this, my output is right here. Okay, V0 of t. Now find the transfer function. So it's the same circuit. Now my output is changed. I will end up with a different transfer function. We'll see that. So I'm going to convert this into S domain. This is 2S, S, this is 1 over S. Okay, these two are in parallel. So 2 parallel with 2S, which is 4S over 2 plus 2S. So 2S over S plus 1. Okay, so I can draw the circuit something like this. This is 1 over S. The impedance here is 2S over S plus 1. Okay, now I can use the voltage division rule. So this is V in of S, this is V out of S. Okay, if I use the voltage division rule, V0 of S equal to V in of S times the same impedance, which is 1 over S over total impedance 1 over S plus 2S over S plus 1. Okay, so V0 of S over V in of S equal to 1 over S. I'm going to do the LCM in the denominator. So S plus 1 plus 2S times S over S times S plus 1. So SS get cancelled out. I will end up with V0 of S over V in of S equal to S plus 1 over 2S square plus S plus 1. Okay, now you can substitute the s equal to j omega. So j omega plus 1 over minus 2 omega square, because we know that j square is nothing but -1, plus j omega plus 1. This is hj omega. This is the transfer function in j omega. I will stop this video here. You should be good to go to solve homework 1 after watching all these 3 videos. Thank you.